With our next talk by Gordon Letwin on the system foundation, we will begin to add significant depth to the concepts just introduced by Mark McAmin in his overview of OS/2. Gordon is known within Microsoft as the father of OS/2. As chief architect for system software, he conceived and designed this operating system. In addition to his fundamental contributions to OS/2, he was instrumental in the development of our DOS and Xenix product lines.
My name is Gordon Letwin, and I'll be giving a talk on system foundation. The talk assumes that you're familiar with multitasking in general, that you have a general knowledge of semaphores, preemption, fundamental scheduling issues. The first part that we need to get into is the API, the Applications Program Interface. This is also called the System API. It's a buzzword that you'll hear pretty frequently. It's basically the technique that programs use to get services from the operating system. It's not just a system call interface. Programs use this technique to get all the services they'll get from everything inside the operating system, including things that aren't kernel-related objects. For example, packages, subroutine libraries, and so on. Like all good buzzwords, the name is kind of misleading. It's not just an applications program interface. It's the only interface to the system whatsoever. Applications programs and system utilities use it as well. All the system interfaces are documented, and they're all documented in this API. There aren't any secret interfaces that some components of the system use to interface to the operating system. Why do we go about using a new API? Why do we create a new API? What's wrong with the old int21? One of the reasons we went to a new API was to get a wider namespace. The int21 namespace just has 256 elements, the numbers 0 through 255. That's a comparatively small number of elements when the API is expanded to include things besides kernel services. Also, it's very difficult for ISVs and third parties to expand the system interface to any degree, since those numbers have to be given out by some master number keeper at Microsoft. Thirdly, we wanted the degree of high-level language compatibility. We wanted high-level languages to be able to call efficiently directly into system services, and high-level languages can't generate int21s. Finally, we wanted a standardized interface to all services. If subroutine libraries needed a call interface, we also wanted kernel services to have a call interface. We didn't want to have a special interface for some kind of services depending on how they're implemented. Also, as a minor detail, the 286 architecture doesn't allow int operations directly. Those would have to be trapped by the kernel, which would be expensive. So we went to a call mechanism. The first thing you'll notice about the system API is that all the calls are by means of dynamic link calls. You've already had a talk from Mark McAmin on discussing dynamic links, so you have a general understanding of what's going on. I'm going to go into it in quite a bit more detail, though, because it's a critical component of the system foundation. Before we talk about dynamic links, let's review static links again. Static links are the old mechanism that we all know and love. Programs calling a subroutine, which is compiled separately. You write your program to call a subroutine. The subroutine is compiled separately. You feed it into the linker, and it produces a combined exe file. The characteristics of classic linking: the target code, and by that I mean the library code, must be present at link time. The target code is then linked into the final exe module, so it's fully in place in that module. That means the target code can't be changed once you've created your final exe module because it's intermingled. The target code, the exe image is quite a bit larger now because the target code is all present there literally. And finally, the target code can't be shared. If you have two separate programs that each use the same library routine, after they've been bound into those two different programs, they've been bound to different addresses, they've been relocated differently. The operating system doesn't understand if that code was in common. The operating system couldn't share that code even if it recognized it because of the different relocation factors. Dynamic linking is quite a bit different from this in some ways. The initial steps are similar. You compile or assemble your main module, you feed that to the linker, you point it to a library routine, what comes out as an exe file, you execute the exe file and everything is fine. So on the surface, dynamic linking appears identical. The key distinction is during that link process, you didn't truly link to the dynamic link code, you link to a special stub that has just names in it. So what you're doing is actually just a named linkage at link time. When you actually run the exe file, the operating system will then find the dynamic link library and do the linkage at execution time. Key characteristics: the target code, the library code's name is present at link time, but not the code itself. The target code is in a separate file called a .dll file for a dynamic link library. The target code can be changed at any time. You just change the contents of the DLL file, then you reload the application program and it gets a new copy of the library. The exe module is smaller because the library code isn't expanded into every exe module. And finally, the target code, the library code, can be automatically shared. The operating system went and fetched it out of the dynamic link library file for each person that's using it. So it's easy for the operating system to understand that a certain library routine has multiple users and to arrange for the pure segments that belong to that library routine to be shared. There are some special data segment services that I'll discuss later that expand this mechanism to provide for service packages. And as a final characteristic, your load time can be a little bit slower because you have to bring these things in. Basically, it's the free lunch principle. The good news about dynamic linking is that you aren't loading everything in one monolithic hunk, so it gives you the opportunity to bring things in piecemeal. The bad news is that you're bringing things in piecemeal and it's a bit slower. Mark Mackaman's talk, he said dynamic linking was a bit faster, and so how do we explain the inconsistency? Mark was actually referring to the fact that if you're dynamic linking to a library package that has already been referenced by some other application, then it's already in memory and the operating system doesn't have to reload most of it. The operating system just shares the existing segments. In that kind of situation, which is a common situation for the most frequently used libraries, it is pretty fast. In the situation where the stuff has to be brought off the disk for the first time, then the load time is a little bit slower, but it's not a significant problem. This slide gives a diagram of the process of load time dynamic links. On the left here, we see the object file for your application. He's calling some dynamic link library just called foo. He declares that as an external reference, and at link time, the linker associates that with the library routine, which defines that external foo. In this case, the library routine says it's in module name dynamic link package, and the entry point name is also foo, the true entry point name. The resultant exe file that you see on the right has the application code, it has the call, which still doesn't have its address fixed up yet since the code's not actually present. And then at the end, in the special load time record, there's a pointer reference to the dynamic link routine that we're looking for. When the operating system loads this package, the exe file comes into memory. You see that on the left. The dynamic link reference is taken by the operating system. The operating system goes through its list of known dynamic link modules. If it's not already in memory, it goes out to the proper DLL file and brings it in, and then does the fix-up at load time. Okay. We also provide a facility called runtime dynamic linking. Runtime dynamic linking is exactly like load time dynamic linking, except that you can generate the name at runtime after you started executing. Your program can start executing, and then at any arbitrary time suddenly decide that it has a desire to call a certain dynamic link library routine. You generate the names of the routines you want to call as ASCII strings, call the operating system, and say, find these guys, load them in for me. The operating system returns you a vector of entry points associated with those names you provided. You then do call and direct via that table at will, calling these routines. When you're done using these routines, you can release the module by means of another special call. This is primarily used when at actual execution time you discover a need to call a particular routine. Commonly, if, for example, you're writing a graphics-related package, a computer-aided design package, and say that there's some very special graphics device that requires a lot of special support, maybe some interaction. If the user suddenly declares he owns one of those devices and wants to use it, you could then at that time create the name of the dynamic link library routine that drives that device, have it brought in, make use of it, then dump it out when you're done with it again. Okay. Library routines need to access data. In the old static link kind of architecture, that was done in a pretty straightforward fashion. The library routine made a reference to the data cells it needed. When the linker fixed that library routine into the exe module, it allocated local static data and relocated the library's references. Everything worked very, very well. In a dynamic link environment, we can't do that. If we have multiple clients for a particular library package, there's no address space set aside in any of those clients' data segments to hold this package's data. The reason for that is because the client doesn't know how much package the data needs. All we knew at actual link time was the name of the package, nothing about the contents of the package. At first glance, this would mean that dynamic link libraries can't have any data of their own. They can only be passed pointers. Well, that's a pretty inconvenient technique. So we've arranged for dynamic link library routines to be able to have two kinds of special data segments, instance and global data segments. Okay. Instance data segments are the most common kind. There's one data segment per client process, and they're automatically initialized when the client comes in place, and they're shared transparently. What this means is, well, pure segments are shared transparently. What this means is that if you have a library routine that has a data segment, every time a new client comes in, you get a fresh copy of the data segment. You don't get a fresh copy of the code segment because it's pure. That's automatically shared by the operating system. The effect you get basically is that everybody has their own private copy of the library, and the sharing that takes place is totally transparent. We arrange for all these data segments for the different clients to all have the same selector so that the code can be fixed up correctly with selector numbers in it. Global data segments are used by packages that need to keep track of a single resource between multiple client applications. There's only one global data segment per dynamic link module. This data segment is only initialized when the first client comes in. When the first client comes in and the dynamic link package is initially loaded into memory, the data segment is initialized. From then on, it's a shared resource used by the dynamic link package. Some subsystems, for example, database subsystems, may need to keep track of a database file that they're managing for several different clients. They want a single global segment where they can keep track of this information, a segment that's not associated with any particular client. I'll go into this in future slides in a bit more detail. Subsystems are more than runtime libraries. They're basically non-kernel service packages. A variety of services really don't belong in the kernel running at privilege level or running at ring 3. For example, a database package. These packages can be provided as part of the operating system and expansion of system services by means of the dynamic mechanism. An example of a library-only subsystem would be VIO. It's a series of library routines that are invoked by the client package, by the client application. They do the work. Some subsystems can actually consist of library routines and task packages. For example, the Windows Presentation Manager not only has a series of dynamic link subroutines that are called by clients, there's actually a presentation manager process that's also involved doing work. OS2 provides a variety of extra subsystem support for dynamic link packages. Number one, as we've already discussed, modules can have global and instance data segments. We've already mentioned briefly that there's special initialization. The module itself is initialized. Each time the first client comes along, the module comes into memory. Also, there's reinitialization for each client, if you wish, so that you can set up special client services. One of the problems you have when you initialize on a per-client basis is the client may fail to tell you that he's terminating. You can be left with a bunch of orphan data structures because clients have died off, they're written poorly, they generate faults and trap out. Maybe they're just careless and don't bother to tell you that they're leaving and they leave unexpectedly. This can cause a lot of trouble. In our database scenario, we can have a bunch of dirty buffers laying around and never get flushed out because we never see any more activity from this client. Because of that, there's a special service called DOS exit list that allows applications, programs, and also allows dynamic link packages to be guaranteed to get control when a client dies off so that they can flush their buffers, clean up, close out files, and so on. Finally, we get to the bottom line, which is the actual kernel system call interface. Some of the entries, all the kernel services are provided through a dynamic link module called DOS calls 1. Some of the entries to DOS calls 1s are actually library routines. They're ring 3 routines that are just called in the same way that subroutine libraries are. An example of this, there's a service that allows you to classify error codes. You get an error code from the system, you can call an entry point, and you'll get passed back an ASCII string in the proper language that's being supported on this release of the system, an ASCII string that explains what the error is, and some codes indicating your recommended action. Is this a system error? Is this a user error? What kind of action would you be recommended to take? So this can come in very handy for an application that sees an error code that it doesn't recognize. That package is actually a very simple subroutine. It takes your error code, it looks it up in a table, and out of that table he gets recommended actions and he gets the text string. The reason why it's a dynamic link library is because that's actually bound to the release of the kernel. If we come up with a new kernel, we'll have new error messages. We'll also have a new library routine in DOS calls 1 that provides these services. The next time you run your existing application, run that binary file, you'll bind to the new library routine with the new messages in it for the new error codes, and everything works out correctly. Some of those entries are actually kernel entries, ring 0 entries. These are implemented through a call gate. You make the dynamic link var call just as you would ordinarily, and unbeknownst to you, the hardware and the system conspire to switch you into ring 0 and provide your services. One of the key characteristics of the fact that some services are ring 3 and some services are ring 0 is we've gone to some effort to make sure that the interface looks consistent. So if we move packages between ring 0 and ring 3, there won't be any externally visible difference. So for example, if you call a ring 3 library with an invalid address, when the library routine tries to reference that address, you'll get a general protection fault and you'll trap out. If you call a kernel with an invalid address, the kernel can actually detect the invalid address and doesn't need to trap you. He can return an error code. But we don't actually do that. If you pass an invalid address to the kernel, we'll also generate a GP fault. And the reason for that is to provide a consistent and stable interface across the entire system. If some kernel functions eventually become ring 3 functions, some ring 3 functions become kernel functions, your program will continue to run in a consistent manner. Okay. We'll talk some about memory management issues now. DOS 1, 2, and 3 were called operating systems, but it's a bit easier, a bit more accurate to view them as loaders and file system subroutine packages. There are a variety of applications. Most applications use them to get themselves loaded into memory, then they control the machine totally on their own, calling the operating system only to deal with the file system. OS2 is actually a true operating system in the classic sense, and then it controls the environment, it manages resources, and it virtualizes the program environment. In other words, OS2 provides a pristine and isolated machine to every individual application. Unless those applications explicitly desire, they won't have any direct knowledge to be able to see the other applications running in the system. The good news about this is that OS2 provides you with a very standardized service. The bad news is that OS2 is required to have strict control over what applications can do. Applications can only do what the hardware and what OS2 allow them to do. The old days of the Wild West kind of arrangement where people would shoot up the operating system by patching it and hooking it, those days are gone. Applications can't perform privileged operations. For example, applications can't address memory that's not been set up for them in the LDT or the GDT. They can't edit or examine the LDT or the GDT. They can't hook interrupt vectors. They can't run at ring 0. They can't call the BIOS directly. It wouldn't do them any good anyhow. The BIOS is real mode code and you're running in protect mode. The BIOS won't execute correctly. And further, they can't do I/O without direct operating system permission. The 286 protect mode hardware brings in some additional restrictions. Programs can't reference beyond the segment's length. They can't put arbitrary garbage in segment registers. You can't execute from a data segment. You can't write into a code segment. And you can't perform segment arithmetic. The environment seems pretty restrictive, and you may think that our general philosophy was kind of a fascistic philosophy. But in practice, our philosophy is actually very libertarian. We allow programs to do anything they want to do which doesn't interfere with other programs. And that's the key aspect of these restrictions. Some of these restrictions I just mentioned, executing from a data segment and so on, writing into a code segment, the OS2 provides some special facilities to get around some of those restrictions. Okay. Talking about memory management functions briefly, there are some obvious functions. You can allocate segments on an arbitrary segment size basis up to a maximum of 65K, the hardware limitation. You can grow segments, you can shrink segments, you can release segments. You can also share segments between processes. There are two basic ways of doing this. One is what we call giveaway shared segments. When you allocate a segment, you tell the operating system that you may wish to share the segment with another application, with another process. Later on, after you've got that segment, you can call the operating system and say, process number 90, I want process 90 to be able to reference my segment, to be able to share this segment. The operating system will arrange that. You then use some other form of inter-process communication to tell your sharing client process that he can have access to the segment, and then you can both reference that shared memory. There's also a mechanism called named shared memory, wherein a piece of shared memory is given a name. Any application that presents that name can have access to that shared memory. The names that shared memory take look kind of funny. They're backslash, sharemem, backslash, and then some name string that looks like a file name. Why do we do that? What we've done there is use the file system namespace to hold shared memory names, and later on you'll see that we use them to hold semaphore names also. We use the file system namespace because future releases of the system will have permissions that are based upon the file system architecture. And our networking is also based upon the file system architecture. This allows us to apply a single permission mechanism uniformly, not only to files themselves, but also to shared memory and the semaphores. It also allows us to implement these things across the network. Semaphores across the network are very, very valuable. Shared memory across the network is probably not valuable at all and probably wouldn't be implemented. But architecturally, it's available. Finally, we have some special services. We have a thing called huge segments to allow you to have pieces of memory that are larger than 65K. The pieces of memory are larger than 65K, but they have to come in these 65K chunks because of the 286 hardware limitation. Basically, what happens is you call up the operating system and say, I need 200K worth of memory. You get back 4 segments. You get back 3 65K segments and 1 segment holding the remainder of the space. We'll give you a base segment selector number, and then we'll give you a spacing value, a segment spacing value. The base number addresses the first 65K segment. If you add the spacing value to that, that new segment selector addresses the next piece, and so on. So you can pretty quickly get to the byte you want by taking its offset in your 200K structure, dividing it by 65K, multiplying it by the segment spacing, and adding that to the base segment number. This is pretty much the segment game that you'd play in real mode, only this one works in protect mode. basically, you can write a program that is also real mode compatible by using the value 4096 in real mode. In protect mode, you have to use the segment spacing you were given from the operating system. Finally, we have CS aliases, which is a technique where you can get a code segment selector that points to the same memory that a data segment points to. So if you have a program that needs to create code and then execute that code, and for example, the presentation manager does that in order to update the screen as fast as it possibly can, what you would do is compile the code you want to execute, you'd store that into a data segment, then you'd call the operating system and ask them to provide you a code segment selector that points to that same piece of memory. So we're actually obeying the rules of the chip, which says that we're not writing into code segments, we're not executing data segments, but we're circumventing that because we have a separate code and a separate data segment that point to the same piece of physical memory and therefore dodge the restrictions. Okay. Another characteristic of memory management in a 286 environment is that we can support swapping and segment overcommit. Swapping is something you're probably familiar with. You have too many applications that want too much memory, you can take some of those applications and swap them out to the disk. We don't swap on an application basis, we swap on a segment basis. In other words, when there's not enough memory, we find a segment that belongs to somebody and swap just that one segment out. The system is virtual on a segment by segment basis, which means that an application has 12 segments that it may be using. 6 of those segments can be swapped out at the moment, the other 6 can be in memory, and the application can continue to run. If it references one of those segments that's missing, the application is suspended, the missing segment is brought on off the disk, the application resumes. He doesn't know what's happened. There's no real way that an application can see segment swapping other than the fact that it runs a bit slower when it has to swap somebody off the disk. The exe file has some bits in it that you can define by means of a loader tool to advise the system as to the status of your segments. You can mark some of your segments preload, which means that when your application is first executed, all those segments will be brought in. You can mark some segments load on demand, which says that the segment was not brought in when you initially start your program. The segment is only brought in if a reference is made to it. Once the segment is in, then these bits really have no meaning. If the segment's being used, it stays in. If the segment is not being used, it may swap out. We have a technique called memory discarding, which is part of the memory management package. Basically, an application can allocate a segment and tell the operating system this is a low-value segment. If you're short on memory, you can go ahead and throw it out. You don't need to swap this data segment. An example of this would be a Windows graphical presentation manager kind of package. You may be putting a pop-up up, and you'd like to save the underlying bit patterns so that when the pop-up goes down again, you can restore the screen, that piece of the screen, to its original image. That saved data is not super valuable data because you can always regenerate it without having to actually have memorized the overlaid bits. So the Windows Presentation Manager would put that data into a discardable segment. When the pop-up window is taken down again, if the data is still available, we just repaint the screen immediately. If the data had been discarded by the operating system, then it will be regenerated by the application. So this is basically a way of telling the operating system that if you've got spare memory, I can find some low-value use for it. If we're tight on memory, then I won't want to thrash the system any more than necessary, and you can reclaim these segments. If there are any such discardable segments, when the system is short on memory, we'll discard segments first to try to reclaim memory. If we can't discard enough segments to satisfy the request, then we'll start to swap. We swap on the classic LRU basis. We keep track of how frequently, of when each segment is used, and the segment that was least recently used is the segment that we think is least likely to be used in the near future, and that is the segment that is swapped out. One of the problems you have to deal with in a swapping environment is to keep track of your memory commitments. You don't want to ever get to a situation where you've started up a bunch of guys, you've got them swapped out, and then you discover you can't continue to run them because they can't all be swapped in. Any one of them can't be swapped in at all. That's a very embarrassing situation. There's really nothing much you can tell the user about why he's put 4 hours of work on his word processor and now the word processors just can't execute any further. Why might we get into a situation like this? Well, first of all, we have a variety of fixed memory commitments. Some of the operating system is fixed in memory and can't be swapped and can't be moved. Interrupt time code, for example, can't be swapped and can't be moved because when an interrupt takes place, we can't bring it off the disk if the code had been swapped out. As a matter of fact, the interrupt that took place might be the interrupt on a swapping device, and we definitely couldn't swap somebody in to service that interrupt. Also, the code that swaps people in can't be swapped out. If we swapped out the swap in code, we'd find ourselves in a very embarrassed situation. We need to save enough memory in addition to the fixed memory to prevent deadlock. Although there are only 4 segment registers in a 286 architecture, there's a situation where you actually need access to 6 segments. The slide here says 5, but that's a mistype. We may actually need to have 6 segments available in memory simultaneously in order to run some programs. The maximum segment size is 64K, so the operating system makes sure at all times that there is 6 by 64K worth of memory that's available. That doesn't mean the memory has to be free. It just has to be available even if we swap people out. So we won't allow people to allocate a sufficient number of segments that we can't either find 6 by 64K worth of free RAM, or we can't make that amount of free RAM by swapping people out. So this really doesn't have a lot of bearing on applications. You'll be refused memory allocation only when we're all out of RAM and we're out of swap space. If you're writing device drivers, though, and you're calling up the system and asking to allocate you fixed memory, we may have to refuse your fixed memory request even though there appears to be plenty of free memory. And if that came about, that would be because it would be overrunning our memory commitment. And then if we gave you the fixed memory you asked for, we could find ourselves in a situation where we could fail to be able to run applications we've already started to run. There are some design issues related to memory swapping, segment swapping, obviously. First is your segment size. Basically, it's like the 3 bears in their porridge. You want a size that's not too small, and you want a size that's not too large. The reason why you want it to be not too large is pretty obvious. If you touch one location in a segment, the entire segment has to come in. This is not a virtual memory paged kind of architecture. This is virtual segment architecture. On the other hand, you don't want to have hundreds and hundreds of 30-byte segments or 200-byte segments because of the system overhead in tracking segments. Typically, a good size might be 16K, 30K, and so on. It actually depends upon the locality and the access pattern of your application. You definitely want to localize things that are used together. Your main command loop, for example, would typically be all in 1 or 2 segments. Your error processing would typically be in a separate segment because you hope the user isn't making a lot of errors and you don't need to call that code very much. Now let's talk about process models. Processes are a key concept in OS2. What is a process? Ordinarily, this would seem to be a pretty straightforward question, and it is a straightforward question in the DOS3 environment. But in an OS2 environment, things can be a bit more confusing. Basically, a process is an independent program. A process is normally associated with a single exe file. All DOS3 applications would be considered a process in this environment. A process in OS2 terms is a unit of resource ownership. Processes own memory, processes own open files, processes own semaphores. The easiest thing at the moment is to view a process as a program, but strictly speaking, a process is actually a unit of resource ownership. To execute processes, there is a couple of calls. There's a DOS exec call, and there's a DOS cwait call. This slide gives you a general idea of the process. In a DOS3 environment, the parent runs for a while, it does an exec of a child. DOS3 was a multitasking environment, but it was serially multitasking. The child had to execute and complete executing before the parent could run any further. So here we see from the arrows, the child starts executing. The child is the sole executing process in the system until the child terminates. Then the parent process takes over control again. OS2 is similar to this in a lot of ways, except that when you do the exec, the parent continues to run and the child continues to run, since OS2 is a fully multitask system. The parent continues to run and the child runs in parallel until such time as the parent decides to wait for the child to find out what his return code is. At the time that the parent does a DOS cwait, if the child has already finished executing, the DOS cwait returns with the child's termination code. If the child is still running, the parent process blocks at DOS cwait until the child completes, then the parent returns from DOS cwait. Another key characteristic is inheritance. DOS2 and DOS3 use this inheritance mechanism, but it's not nearly as significant in their environment as it is in this environment. This picture, for example, shows a simple form of inheritance. The standard in and standard out file handles are inherited by the child process. Child processes inherit file handles, they inherit a parent's priority, they inherit a parent's screen group, they inherit quite a bit of information from a parent. File handles are the most significant thing, and I'll concentrate on those. In this particular case, the first parent was interactive. It was reading from the keyboard and it was writing to the screen. The child process inherits those same handles, so if the child process wants to read, it will read from the keyboard, and the output from the child process will be written to the screen, properly intermingled with the parent's output. Here's an environment where the parent is reading and writing from a file. Maybe it's a batch file process, maybe it's an assembler of some kind, or just in general some application utility program. In this case, the child program, the same child program with no binary changes whatsoever, when he runs, he inherits the handles again, only now he inherits the file handle on the input side and the output file handle on the output side. The child automatically gets its input from the correct spot, the child's output automatically appears on the correct spot intermingled with the parent's output. Here's a more complicated situation where a grandparent process has created anonymous pipes that we'll discuss briefly later to run a child process, his child process labeled parent here, to do work for him. If that parent process in turn decides to fork off to create a child process to do work for it, then that child will inherit the proper handles, which are the grandparent's pipe handles, and once again the child's output will be properly intermingled with the parent's output. This is a pretty hardcore slide. This is basically the mechanism necessary for a parent to create a child process and have that child not inherit the standard handles. I won't go through it in great detail other than to say that basically you use the dupe mechanism to do a name shuffling arrangement. So the parent shuffles his standard handles to temporary files, opens up the files he wants the child to inherit on his standard handles, executes the child, and the parent then restores his handles. Okay. As we've seen, parents can execute child processes. Those child processes themselves can execute further child processes. The process can be arbitrarily nested, arbitrarily deep. For this reason, we have something we call command subtrees. A command subtree is basically the mechanism where a process can execute a child to do work for it. And then it can describe that child and any descendants that child may have as a single concept. A parent can say, kill this child and all of his descendants. The parent can say, change the priority of this child and all of his descendants. The child doesn't even need to continue to be executing for this to take place. So long as some of those descendants are taking place, that piece of work that the parent initiated is still taking place on behalf of the parent. The parent can still control any processes that are involved in executing that work. That's basically the concept behind command subtrees. Now let's talk next about threads. After we confuse this with a process, we have another concept we call threads. Well, what is a thread? It's kind of hard to describe a thread. It's not that DOS 3 didn't have threads. DOS 3 does have threads. It's just that they were never noticed because they were taken for granted. When a program executes, the CPU executes instructions in the correct order. If there's an interrupt or a context switch, the CPU is pulled away from that instruction stream, but later on it returns right where it left off. The register contents are restored and the execution continues unaffected. This passage of the central processing unit through the code is called a thread of execution. We have a special term for the progress of a CPU through a series of code instructions because OS2 allows more than one thread per process. A program basically can have more than one CPU executing at the same time. We're not referring to the automatic sharing of pure code segments. If you run 2 copies of a certain program, the operating system doesn't bother bringing in 2 copies of the code, it just shares that. That's a transparent trick pulled by the operating system. We're talking about 2 CPUs, in effect, executing a single process, manipulating a single set of data. So, for example, if one thread opens file handle on a file and gets 4 back, another thread in that same process can read from that handle and get the proper data. We obviously don't really have more than one CPU. We're using context switching. But because of the fact that our scheduler is a preemptive scheduler, the proper model to use when you design your programs is to assume that all those threads are executing simultaneously. Why would you want to have more than one path of execution to a program? What's the point of that? Well, for one, a program like a spreadsheet may be told by the user to modify some cell that requires some time-consuming update. In a current implementation, in a single-thread implementation, the CPU is off doing that update, and the program isn't sensitive to further commands until it's done. In a multi-threaded environment such as OS2, one thread can run off doing the updates, and the other thread can go back and read more commands from the user. Say that the user said he wanted to do a data write. It was a large write to a disk, or perhaps it's a write to a plotter that's going to take some time. A thread can be dedicated to doing the write command, and another thread can come back and read commands and continue to run the application on behalf of the user. Note that the OS provides no exclusion between these threads. All these threads are separate but equally executing the same program. So long as each thread has its own stack, so long as the thread is only doing things that are pure, in other words, don't modify any static data values, or that only modify stack frame variables, then there's no crosstalk between the various threads and they can run without any concern. As soon as one of these threads wants to modify a static data location, then there needs to be some sort of critical section interlocking as part of your application to keep multiple threads from stepping on each other's toes. We suggest use RAM semaphores for this technique. They're designed primarily for this purpose, and they're very fast and they're very efficient. Threads are the schedulable resource for the operating system. Threads don't own hardly anything. We've mentioned that processes were the unit of resource ownership. Threads only own their general purpose registers, and they also own a set of floating point registers, and they own a priority value. Individual threads can have separate priorities within a process. Threads are invisible outside the process. There's no way to tell if a process is using more than one thread. There's no way to query or modify a thread within a process. There's no way to change the priority of a particular thread outside a process. Within the process, you can manipulate your threads individually, but from outside the process, threads are invisible. Finally, you can have multiple threads inside the kernel. In other words, a process that has multiple threads can use one of those threads to do a read and can use another one of those threads to do a semaphore wait, for example. In fact, it's very common for a multi-thread process to have a couple or more of those threads blocked on semaphores, and they're all inside the kernel doing that blocking. I'll take a moment to talk about some special process issues that come up in an OS2 environment that weren't present in the DOS2 and DOS3 environment. One of the most important ones is screen keyboard usage. It's important that basically you look before you leap. The system model is that processes inherit standard in and they inherit standard out. They need to do their input from standard in and their output to standard out. And that's the fundamental model, and that's all that processes should ever do. Now, it turns out there are some minor details problems that come up with that model. Standard out, trying to write to a high-definition graphic screen is very, very tedious. There's no architected mechanism to discuss a two-dimensional presentation. There's nothing for color. You definitely don't want to generate a full-color, high-resolution image by means of escape sequences through standard out. So instead, we provided a mechanism called VIO, and we provided the presentation manager to provide you with a great deal of services for writing to the screen. But these services architecturally are special cases to talk to a specific device, the screen device. What your application needs to do is to look to see if standard out is pointing to the screen, and there's a call to do that. If standard out is pointing to the screen device, then you're welcome to avoid using standard out and use special direct-to-screen interfaces such as VIO and Presentation Manager. If standard out does not point to the screen, then you must not use the VIO stuff directly. Instead, you must use standard out. Well, for a lot of programs, it doesn't make sense. If you come up with a WYSIWYG editor that wants to go into graphics mode and you discover standard out is pointing to a file, then what you do in that case is you put up a message just saying this is silly on standard error and just terminate your process. But you do need to verify that you really are expected to write to the screen, and that means your standard out points to the screen before you start writing to the screen by means of the VIO or Environment Manager, Presentation Manager package. Signals are another special thing to deal with. We have Control-C, we have kill, and we have flag, 3 different kinds of signals. Signals are very similar to the Unix signal concept. They're basically a software interrupt. The Control-C takes place when a Control-C character is hit and your process has indicated he's sensitive to Control-C character. At that point, a software interrupt takes place. Basically, the CPU is stopped wherever it's executing inside your program. It starts to execute at an address that you supplied. You can do whatever you wish to do at that point and then resume executing back from where the CPU is interrupted. Or if you want, you can just leap back up into your command loop or something and put up a new prompt and continue reading commands, whatever it is you wish to do. You're allowed to intercept the kill process. When your process is killed externally, we generate what we call a kill signal, and if you wish, you can intercept that. That allows you an opportunity to close your files, to clean things up. In general, if you're, say, a database program and you're in the middle of collapsing a database, you may want to postpone being killed a little bit so that you don't leave the database in a corrupt fashion. It's perfectly possible for your application to intercept sig kill and then refuse to terminate. You're expected to clean up and then terminate as quickly as you can. But if you fail to terminate, if you just clean up and sit there in a loop or go back to command mode or something, there's nothing the OS can do to prevent that. So you've basically produced an unkillable program if you do that. That's not a good thing to do. The users will be able to figure out which program it is that's its fault. It's the program they can't kill. So there's nothing OS2 does to prevent that, but it's a bad thing, and the failure of your application will stick out like a sore thumb if you fail to process sig kill correctly. Finally, there's a mechanism called sig flag. It's a form of inter-process communication where one process can basically send an arbitrary flag signal to another process. In general, it's a very narrow mechanism. You're only sending one bit of information. What's special about it and what gives it value in some specialized cases is the fact that it's an asynchronous mechanism. You're actually kicking the receiving process in the rear end, and he's forced to pay attention to you right away. All the other forms of IPC, the message is presented to the receiving process, but until the receiving process looks at the message, it's not seen. Finally, a remaining special issue is exit list. We discussed DOS exit list briefly before when we talked about applications or dynamic link subsystems. Exit list is similar to the sig kill arrangement and allows you to get control as a process is terminating. But there's a key difference. Sig kill is only used by the process itself. Dynamic link library shouldn't use sig kill. There can only be one sig kill recipient. So if a dynamic library specified its own address for sig kill, then that would lock out the application. That would destroy the application's registered sig kill address, and the application wouldn't run correctly. Instead, dynamic link libraries that need to get control at termination time should use exit list. Applications can also use exit list. Multiple addresses can be registered through exit list. There can be an arbitrary list of addresses. When the program terminates for whatever cause, we'll start calling down through that exit list of addresses one at a time, allowing them to clean up after themselves. If one of these exit list routines generates a general protection fault, then that's it. We've had two problems. The process is dying, presumably because it's unhealthy, and then we started to call the exit list routines, and some of those are unhealthy. At that point, we'll even stop executing the exit list if necessary. We mentioned we have a multitasking-based, priority-based scheduler. It's a preemptive priority-based scheduler. What that means is that at any arbitrary time, the CPU can be taken away from any process and assigned to any other process as necessary. That's basically done on a priority basis. The highest priority process that wants, actually the highest priority thread, scheduling is all done on a thread basis. The highest priority thread that wants service receives service. When that thread no longer needs a CPU, then the next highest priority thread can have it, and so on down. If no thread wants to run, then the system will hold the CPU in an idle loop. The scheduler algorithm is reasonably straightforward. There are three static priority classes. There's a high priority class, which is called a time critical class. Basically, any thread running in that category of priorities gets the CPU whenever he wants it. The priority of that thread is never changed, isn't affected by which processes are in the foreground screen group and which processes are in the background screen group. The behavior and CPU consumption of those threads also never affects its priority. Basically, the time critical things should only be used by very special applications that will cause significant failure if they fail to get service in a particular period of time. One example might be a network protocol where if you don't respond to a query packet within some short period of time, a few seconds, your network connection is taken down. In that case, your responder routine should run in a time critical priority. Another example might be some real-time related things where there's a robot arm that's coming down on this car, and after you interrupt an optical beam, you have to stop that arm within a tenth of a second, or else that process should be a time critical process. Anything else should run in the middle category priority. Before I talk about the middle priority category, to be symmetric with the force run high priority category, there's also a low priority category called the idle category. Basically, processes whose priorities are in that category only get service if nobody else wants service. The middle category is the most interesting one, and that's a dynamic priority category. Basically, your average process runs in this priority category, and where it lands in that priority category depends upon a couple of things. If you're in a background screen group, in other words, the process is associated with an activity that the user is not communicating with on the screen, then you have a lower priority. If your process is associated with the foreground screen group, then you get a higher priority. Finally, if your process is the one that's actually interacting with the user, it has an even higher priority. This is done basically to give us maximum response. Your typical multitasking operating system is designed to maximize system throughput and to maximize fairness among multiple users. Well, this is a single user system, and throughput's not an issue. Over the course of a day, the CPU is going to be idle 99% of the time. Our major concern is maximizing response. So if the program you're interacting with wants the CPU, he gets the CPU, unless a time critical guy needs it, even in advance of that. Then if there's any time left over from the thing that you're actually interacting with, we'll use that to run background processes. This is also a dynamic priority kind of arrangement. The lower order bits of your priority will be affected based upon your I/O behavior and your runtime history. This is a classic optimization meant to optimize system throughput. So if you have an I/O bound guy and a CPU bound guy, the I/O bound guy gets little slices of time so that he can keep the disk busy. We do have that kind of optimization in the scheduler, but it only applies to processes who are very, very close in priority. So it's impossible for a background application, for example, to get a boost based upon his behavior, a high enough boost to make him run in preference to a foreground application. If you have multiple background applications and the foreground guys don't want the CPU, then we'll adjudicate between the background guys using these lower priority bits to try to optimize system throughput. OS2 contains a variety of inter-process communication features. One of them is anonymous pipes. We mentioned that briefly a while ago. Anonymous pipes are very similar to the Unix concept of anonymous pipes. A pipe is basically a direct connect mechanism where a handle that belongs to one process doesn't write to a file, it doesn't write to a device. Instead, it writes to an internal kernel buffer that is associated with another handle belonging to another process. So one process can write data out onto a handle, another process reads the data back from the handle. Name shared memory is a form of inter-process communication we've also discussed. It's very, very efficient, but one needs to have your own special protocols in that shared memory, obviously, to communicate with your client processes. Giveaway shared memory, we've discussed that, and then there's also a queue mechanism. Queue mechanism is kind of like a structured pipe, in that you write messages into the queue mechanism, and those messages are received by the queue receiver. The messages have priorities and so on, so that the receiver can say he wants to read the messages in first come, first serve order. He wants to read the messages in priority order. The receiver can specify particular messages if he knows that there are some messages in the queue for him. The sender can specify a special flag that says that he wants acknowledgement when the receiver takes this message. So it's a higher level of structured kind of pipe mechanism. We have RAM semaphores, which are a form of inter-process communication. One of the problems with RAM semaphores is there's no keeping track of who the owner is. So if you take a piece of shared memory that two processes have access to, and you use some of the locations in that shared memory for RAM semaphores, it's a risky operation. If one process claims the semaphore and then dies unexpectedly before it has a chance to release the semaphore, then the other process will just never get the semaphore. It'll be blocked forever, and your particular application will be hung. You can't say that, well, I'll just use DOS exit list, so if the first process begins to die, he can see that he owns the semaphore and releases it, because there's no ownership related to the semaphore. The first process can't tell whether or not the semaphore, which he sees as claimed, whether it was claimed by him or claimed by somebody else. You can't write down a value, an additional static variable that says that I'm the one that's claimed the semaphore, so if I find myself in DOS exit list due to an unexpected death, I can release the semaphore. Because then there's a race condition. You either say you own the semaphore but haven't claimed it yet, and if you were to die right then, you'd release the semaphore when you shouldn't. Or you claim the semaphore and then write down in your own memo pad that you own the semaphore, and if you were to die between those two events, then you would fail to release the semaphore when you should. So there's always a small chance with RAM semaphores that if multiple processes using RAM semaphore, you can orphan the semaphore and leave it set when one of your process dies. The primary function of RAM semaphores was to manage resource contention between multiple threads of a process. When a process is dying, all the threads are dying. And the fact that the semaphore was left set, it becomes meaningless because that memory is going to be destroyed shortly anyhow. If you're going to be needing semaphores between multiple processes, and that's a very common situation, you need to use system semaphores instead. System semaphores are a little bit slower than RAM semaphores, but they're still pretty rapid. I believe the number is on the order of 200 or 300 microseconds to set and test a system semaphore. The advantage of system semaphores is that they're owned. They have orphan recovery mechanism. When the system sets a system semaphore is set, it also writes down who owns that semaphore. If a process dies owning a semaphore, the system recognizes that and makes some special marks. So later on, when somebody else comes along and says, I want to claim this semaphore, they get a special code back saying, the good news is you can have the semaphore. The bad news is the previous owner died while holding it. It's kind of an estate sale of semaphore arrangement. If you come back from a system semaphore call and you get this code saying you own the semaphore because the previous owner died holding it, what you should do really depends upon your application. If the semaphore is protecting some database, then you know the database is probably corrupt. You can print up a message for the user and terminate. If you wanted, you could exec a child process that might clean up the database or whatever is necessary. If instead you were owning the semaphore you claim just allocates contention among, say, some special printer device, then maybe it's not really a problem. You'll just send a couple of line feeds to push that junk off the page and then go on about your business. And it's not a concern that your previous owner died in use. System semaphores can be operated in a variety of different ways. And these ways are basically orthogonal. So when you read about system semaphores, you'll see a variety of interfaces, and they're kind of confusing. The thing to remember is that there's really two different models that you might want to use a system semaphore in. One is a counting model, which is used to protect the critical section. You get into a critical section, you set the semaphore. When you're out of the critical section, you release the semaphore. That allows you basically to control contention between a particular single resource. You can also use that in a counting fashion so that if you recursively call routines inside yourself and they also try to claim the semaphore, that you won't block because you already own the semaphore. Instead, an account will be increased. So if you claim the semaphore 5 times, the semaphore is owned by you until you've released it 5 times as you wind back out of the recursive list. The other technique that is used for system semaphores as a flagging technique, where a semaphore doesn't actually protect the critical section, but instead is used as a technique to flag or semaphore other processes that certain events have taken place. You may have a process that's waiting for a certain key to be struck or a certain event to take place. If some other process sees this event and wants to flag the first process, it would use a system semaphore to do that normally. But in this case, we're not actually watching a critical section. Instead, we're flagging events. And that's why we have these various services where we can force a semaphore set, we can force a semaphore cleared, and so on. Those calls are used in a flagging kind of mechanism. Signals are a form of inter-process communication. We discussed that briefly. The signal mechanism is a very narrow form of inter-process communication, but it's the only truly asynchronous form there is. Finally, there's DDE, which is dynamic data interchange. The presentation manager supports DDE. It's basically a mechanism very similar to the DOS int2F mechanism for those that are familiar with it, wherein a variety of applications can register themselves as providing services and information through this interface. Then in a symbolic named fashion, a new application can come along and say, I want to talk to somebody that provides the services, and here's a message or a bunch of data I want to send to that guy and get a response from. So DDE is basically a form of a communications clearing agent supported by the presentation manager. Well, you've seen all these 90 different kinds of inter-process communication. How can you ever decide which ones you want to use? So we've prepared this chart to give you sort of a general overview of what the various features and advantages and disadvantages are of the forms of inter-process communication. Anonymous pipes are a handle interface, which means they're transparent to programs. Programs just read from standard in, they write from standard out. They don't know they're dealing with a pipe. So if you want to talk to if you want to use an arbitrary process, an arbitrary program to do work for you, then you can talk to it through anonymous pipes, and it isn't even aware that you wanted to do this and has no special support code in it. Disadvantage of anonymous pipes: number one, they're strictly serial. Data has to be copied into the kernel space and out of the kernel space, which takes some time. And of course, the processes must be related. You can only talk to a child process, or with some effort, you can talk to a grandchild process. Shared memory is a form of inter-process communication. It works out really well because it's random access. There's no copying. It's very, very efficient. You're actually looking at the same memory cells in each case. Disadvantage, though, is that it needs a private protocol. All we provide is the shared memory, and as to what the messages look like and how you can tell if the message is written, how you can tell if a message is read, that's up to the two applications. Finally, there's no data protection. If a client, somebody you're sharing memory with, has access to the entire segment, you can't just give them access to part of the segment. If he goes crazy, he can wipe out the memory that you're sharing and perhaps do some damage to your application. There's a queue mechanism as another form of inter-process communication. Disadvantages are that it's a message interface and it's a high-level interface. You can get your requests in priority order, you can send responses and so on. Disadvantages are that it's another special interface. You need special code in your application to use it. There is involved some degree of data copying, and there's some degree of subsystem overhead. RAM semaphores, form of inter-process communication. The advantages are they're very, very fast. Disadvantages, we discussed at some length, they're unsafe for inter-process communication between multiple processes, unless you're in some environment where you know for sure that the unexpected death of a process and the orphaning of a semaphore won't cause you grief. System semaphores are reasonably fast, and that's not a disadvantage. It's a mistype on the slide. Another advantage is that they're fail-safe. Disadvantage is, once again, that they're reasonably fast as opposed to very fast. Signals and advantages that they're asynchronous, but they're very, very narrow, and of course they require cooperation on the part of the recipient application. If you send an IPC form of a signal, a SIG flag, to an application that doesn't expect it, nothing happens. That's it. That way practical jokers can't flag processes that are unsuspecting and do them some damage. Dynamic data exchange, it's a very general and flexible mechanism, and it's a symbolic mechanism. You don't need to know the process ID of who you want to talk to. You just need to know the name of the service you want provided. Disadvantages, though, is there's additional overhead involved in that kind of service. It's the old free lunch principle again. Okay, file system support. OS2, unfortunately, still doesn't really solve very well the large disk problem. We have a half solution in this environment, and the reason why it's only a half solution is primarily a schedule hit. As throughout the process of OS2 development, we'd find that we're up against major scheduling constraints. Some meetings were held where we talked about reducing some of the functionality in the product, and it turns out that there was tremendous hewing and crying, and nobody involved with the project at all wanted to leave out the new extended file system, but it was left out because you can live without it, and you can't live without multitasking, we can't live without real mode support, and so on. So the good news is that we do have multiple partitions on a disk, so you can take your 60 megabyte hard disk and treat it as two 30 megabyte disks, treat it as C and D, and use it successfully. The bad news is you're still limited without special driver support to 32 meg disk drivers. If you write a special driver that uses larger than 512 byte sectors, then you can indeed go to larger size disks. People are doing that today. And finally, there are some additional services having to do with timed response. This is a multitasking system. Processes can sleep. Processes can wait for timer events. So there is a function called the sleep function where threads can pause for an arbitrary period of time in milliseconds. Our clock resolution is 32 hertz, which means we're talking about a 30 millisecond resolution for sleep times. There's also a service called DOS timers, so that at periodic intervals you can have a semaphore set or cleared by the operating system. So that allows you to synchronize events. It allows you to set up a thread that says if nothing happens within 2 seconds, then wake me up and I'll complain to the user and so on. And so those services allow you to interact with the user and have a time sense about you as you do so. Okay, a summary of the topics discussed. The system API, it's done through dynamic linking. Dynamic linking is very much like static linking, only it's done at load time. A variety of advantages are provided by that. Memory management, we have dynamic memory management. We have virtual memory on a per segment basis. We have swapping. Processes, the unit of resource allocation, see them as programs. Multiple processes that can run each other to do work for each other. Within those processes, you can have multiple threads of execution taking place at one time. The scheduler is priority-based. There's a time-critical category and a normal category. There are a great many forms of inter-process communication. File system has been enhanced to allow multiple partitions to be multiple DOS partitions on a single disk, and a variety of time-related timer services are provided. As a conclusion to my talk, I thought you might be interested in this rare slide produced from the Letwin archives. This is a very, very early version of DOS OS2, a multitasking DOS. As you can see, we had some bugs to work out. We eventually got the thing shrunk down considerably, and the product that you see today runs on just one machine.
For additional information on the topic we just covered, be sure to take a look at the written questions and answers that accompanied this videotape.